Hello everyone, this is our mission briefing for Jason-3 to be launched aboard a SpaceX Falcon 9 rocket on Sunday, January 17th. We're here now to talk some about the Jason-3 mission, and here to do that with us is Laurie Miller, the Jason-3 program scientist and chief of the NOAA Laboratory for Satellite Altimetry. Josh Willis, the Jason-3 project scientist from NASA's Jet Propulsion Laboratory. Mark Cohen, Associate Director and Chief of Low Earth Orbit Programs for EUMETSAT. And Sophie Coudenfay, Chief of the Altimetry and Precise Positioning Office for CNES. And we'll begin first with Laurie Miller. Laurie?
Thank you. Good afternoon. I'm glad that you can make it to our briefing. This is an incredibly exciting moment for us. After 7 long years of preparation, we're just now about to launch Jason-3, the latest in a series of U.S.-European missions designed expressly for monitoring sea level rise, one of the clearest symptoms of global warming, but also to help NOAA forecast hurricanes and El Niños and other extreme weather events. So regarding the climate problem, it's now generally understood that we've entered into a new era, a new norm, marked by rapid and persistent changes to the entire whole Earth system. But what may not be widely understood is the role of the ocean in this complex process. And so here's a really incredibly startling fact. More than 90% of all of the heat now being trapped in the Earth's system due to the greenhouse effect is actually going into the ocean. This makes the ocean perhaps the biggest player in the climate change story, but it also helps explain the importance of the Jason mission, because Jason allows us to get the big picture in terms of sea level change in the years to come. In terms of severe weather, well, you don't have to look very far to find examples. Heavy rainfall, flooding, tornadoes out of season, droughts, all of these may seem like separate, isolated events, but many, if not all of these, are actually connected, linked in a fashion, to changes in the ocean occurring half a world away. The massive turbocharged El Niño that's currently battering the U.S. is perhaps one of the best examples. I have a video that shows the conditions in the Pacific right now. And the video shows an area of high sea level stretching from the west coast of South America practically all across the Pacific Ocean. This is the result of a drop-off in the trade winds, allowing a massive shift of water to flow backward along the equator. This causes a suppression of the upwelling in the eastern Pacific that normally keeps that part of the world cool. But in this case, it sets off a chain of events that ultimately causes higher sea surface temperatures and changes in the weather patterns at mid-latitudes. And in fact, the severe weather that I spoke to you a moment ago. NOAA is using this information, of sea level information, in its forecasting models. It assimilates the Jason information into its seasonal forecast model and is able to predict El Niños, sometimes with remarkable accuracy, many months in advance. NOAA is also using this information to help forecast other types of features, like hurricane intensity, and track oil spills, and develop high seas wave warnings. But I think you get the big picture. Jason information is incredibly useful, especially to NOAA, because it allows us to not only track the sea level change that is impacting our coastal features right now, but also to help forecast extreme weather. So let's get on with it. Let's light that rocket and launch Jason-3.
Thank you, Laurie. And next to Josh Willis, the Jason-3 project scientist from NASA's Jet Propulsion Laboratory. Josh?
Thanks, George. I'm extremely excited to be here. This is the culmination of a long process for me. I started using data from the predecessor to Jason-3, Jason-2, and before that Jason-1, and before that Topex Poseidon, launched in 1992. I like to say that Topex is the satellite that got me my PhD, so I wouldn't be sitting here if it wasn't for the really amazing capabilities of these satellites. The satellites are really an incredible technological feat, despite the fact that you might have heard that Jason-3 is very much like its predecessor Jason-2. This is a good thing, in fact, because what we're trying to do, as Lori alluded to, is build a record of the climate. So we would really like our missions to have continuity and to be very similar from one to the next. And Jason-3, much like its predecessor Jason-2, will be able to measure the height of the ocean in an area that's about 6 miles across, from 800 miles up, with an accuracy of about 1 inch, so about the width of a quarter. So it's really quite an amazing feat, and if you average the data from one of these cycles of the Jason-3 or Jason-2 missions, you can actually get an accuracy for the levels of the ocean as a whole to within better than half a centimeter, so really small. So we can really see the rise of the global oceans, and also, as Lori mentioned, this is one of the most important yardsticks we have for human-caused climate change. With all the extra heat that's being absorbed by the ocean, the waters are expanding, and of course they're collecting the extra runoff from melting glaciers and ice sheets, which are also reacting to the warming climate. So these two things together cause global sea levels to rise. And in fact, that global rise is really our most powerful tool for measuring human-caused climate change. But these missions were not really designed originally to measure climate change, although that's now one of their primary functions. Originally, they were designed to measure currents. That incredibly high accuracy of measurements of the height of the ocean tells you about where the currents are and how fast they're going. Whenever there's a large current in the ocean, it literally tilts the sea surface, and the satellites were designed to measure that tilt. Now, the higher sea level is also often a result of warmer water. Warmer water literally stands higher than colder water, and this is a large part of the signal that we expect Jason to measure. And in fact, this is incredibly important for things like El Nino. I have a short video of a loop showing the El Nino of this year compared with the last really large El Nino event in 1997. And if you watch the 1997 one play out on the left-hand side, the reds and whites designate high sea levels, and in the eastern Pacific, near the coast of South America, you have high sea levels that are almost a foot higher than normal. This year, we see a very similar evolution of this El Nino, and that's important because the 1997 event brought about twice the average rainfall for California and twice the average snowpack for California as a normal year. So the Jason missions are an incredibly powerful tool, not just for measuring global climate change, but also for watching the evolution of these things like the so-called Godzilla El Nino. And without them, we would really be turning a blind eye toward our oceans and our climate. Thanks.
Thank you, Josh. Now to Mark Cohen, the Associate Director and Chief of Low Earth Orbit Programs for EUMETSAT. Mark?
Thank you, George. Good afternoon. I'm very, very glad to be here and just coming to the launch of this adventure, which involved all partners across the world, NOAA, NASA, CNES, EUMETSAT, and also all the industry. As you know, EUMETSAT has the objective with its partners to deliver integrated data, in particular to the marine community. And operational oceanography, like the operational meteorology, is about delivering relevant and reliable information services to both citizens and decision makers. So today we are already in EUMETSAT together with our partners. We are contributing to the development of operational oceanography through several missions, Jason-2, also our mandatory programs like METOP and Meteosat, which we also do in collaboration with the US, and also from other missions from the international partners. Products are extracted in our facilities, but also a bit everywhere in Europe. And they are distributed via a system called UMETcast, and also are available through an Earth observation portal. In the future, Jason-3 will be the reference for cross-calibration with other ocean altimetry mission, and in particular the Jason-2, but also the Sentinel-3, which will come up soon in 2016. UMETSAT will provide these products with its partners, which can be ingested in the ocean models, and we will. In our strategy, we plan to enhance this service towards the years 17 with further Sentinel-3 satellites, and later on with the follow-on of Jason-3, which is the Jason-CS Sentinel-6. So the UMETSAT is very excited in having this satellite launched because it's part of a long-term strategy of having these precise ocean altimetry missions over a long period of time, and Jason-3 is a very important element to complement Jason-2 and to prepare for the future. Thank you, George.
Thank you, Mark. Now for comments from Sophie Coudenfay, the Chief of the Altimetry and Precise Positioning Office for CNES. Sophie?
Thank you, George. So in this adventure, CNES has taken the role of coordinating the system with a partner and developing the satellite with Thales Alenia Space, French industry, who was our prime contractor. So this is a long product line because we also developed Jason-1 and Jason-2. Now we are going to handle the operation of the satellites when it will be separated from the launcher. So a few days after this separation, the satellite will be ready for operation, but it has to reach the orbit of Jason-2. It will take 17 days. Then we will fly between 1 minute and 10 minutes behind the Jason-2 satellite, depending on the dispersion at the injection of the satellite. And then we will intercalibrate the data between Jason-2 and Jason-3. As Josh said, it's very important because it's an high accuracy mission. It's very important to intercalibrate all the instrument and the product. And then 6 months later, we will move the Jason-2 satellite on an interleave orbit so that we have a better coverage of the ocean. I think that's it for me.
Thank you, Sophie. We'll take questions now, and we'll begin here with questions here in the audience, and then we'll take questions on the phone, and then we also have a way to take questions from our social media friends. If they go to #AskNASA, they'll be able to send us questions as well, which our panelists will answer. So we'll start. Please wait for the microphone to come to you and give your name and affiliation if you would. And we'll start right here in the front.
Hi, Stephen Clark from Spaceflight Now. A couple of questions. One maybe for Lori or Mark. Can you give some examples of how ocean data from the Jason series of satellites is used operationally? What sort of applications are there? Forecasting, and are there also commercial applications for maritime shipping and things like that? And also just a question on when you plan to launch the first Jason CS satellite as a follow-up. Thanks.
You take the question?
Yeah, I'll talk briefly and then pass it to Mark.
Yes.
I think one of the simplest and clearest examples of the application of the Jason data to marine operations is in terms of being able to detect significant wave heights, high wave heights. This is a sort of a bonus measurement. It's not the sea level measurement, but it's another measurement that the radar system is able to make. And NOAA uses this information by supplementing what the models produce in terms of the wave fields. The forecasters actually overlay the satellite data on top of the model fields and are able to verify in real time what the models are showing. And so this is a critically important part of the National Weather Service's service to mariners and also to coastal areas that need to know what conditions are about to become hazardous in terms of marine operations. The applications that Josh was referring to in terms of monitoring currents is another area which is widely used, perhaps not as widely recognized. We're able to essentially determine the currents much like meteorologists are able to determine the wind patterns in the atmosphere. The altimeter data provides us with the same sort of information. So we put the data into the numerical models, and out comes essentially a gridded field of currents that can be used then for understanding, for example, the oil rig operators in the Gulf of Mexico. They need to know when currents are going to exceed a certain threshold value, because then it poses a hazard to their operation. And that information can come out of the models being fed by the altimeter data. So we can give them essentially hour-by-hour updates that tell them when it's dangerous to operate and when it isn't. So those are two examples of what I would call near real-time or real-time operations. And then there are a lot of others, but I think Mark should take it from there.
Yes, maybe I can complement on the Jason-CS question. So we are going to launch now the Jason-3, which has a design lifetime of 5 years, which leads us to 2021. The current plan is to launch in 2020 the Sentinel-6 Jason-CS, which is a Copernicus mission at that point in time, and to have an overlap of 9 months to 1 year with the Jason-3 in order to do intercalibration, because it's a new satellite, so we need more time to do intercalibration, and then to take it from there. And again, the operations of Jason-3 and of Sentinel-6 are in Europe are under the Copernicus program, which is financed and funded by the European Commission. Thank you.
More questions here in the audience.
Hi, Philip Slauson, NASASpaceflight.com. I think this is for Sophie. Post separation from the launch vehicle, you talked about 2 days. You'll be ready for operations after separation, and then you have 17 days to get to the target orbit. In what sequence are you going to be doing the deployments? Is that going to be in that initial 2-day period where you're going to be deploying the solar arrays? And then as you move towards the target orbit, are you going to be doing any, taking any test data, doing any altimetry just to test that the instruments are working? Thank you.
Yes, in fact, we switch on the full payload during the 3 first days, and then we start to measure the distance between the satellite and the water, but it's not on a regular track, so it's not useful for scientists, but it's useful for us to calibrate the instrument. Okay.
Hi, good afternoon. Matt Camlett, CBS Los Angeles. For Mr. Miller, one of the more visible phenomenons we've been seeing, especially along the coastline in Southern California, has been the unprecedented number of sea lion pups washing on shore. The implication, and well, the fingers pointed mostly at the change in temperature of the ocean. Do you expect this mission to shed any light on this phenomenon?
Well, I think it'll shed light on how this particular El Nino event will decay. We're near, or probably close to the maximum, and we're anticipating, based on NOAA's forecasts, that it will decay slowly over the coming months. So in that sense, I think that there's going to be a slow abatement or decline in the kinds of phenomenon that you're talking about. But there's another problem that's a more general problem, and that relates to the fact that we're heating up the oceans. And this is actually causing real dislocations in a lot of the fisheries. So for example, fish schools that used to be in one location are now moving northward because they can't stand the higher temperature water. And this is causing a ripple effect in ecosystems. So the sea lion pups that you're talking about are partly suffering because of this, but they're just one manifestation. In fact, there's just a gigantic amount of dislocation going on in terms of the world fisheries. And that's going to be a consequence that it's happening right now, but it's going to get more severe, and considering how much of the human population depends on protein from the ocean, I can see this becoming a problem in the very near future.
If I could just add to that very quickly, you really have three things going on in the oceans right now off the coast of California. You have global warming, which has been going on for about 18 years since the last really large El Nino. You have the El Nino, which is unfolding right now. And the third potential one is a switch in what's called the Pacific Decadal Oscillation. You can kind of think of that as El Nino's bigger, slower moving brother. It takes about 20 years or so to switch from a cold phase to a warm phase. And for about the last 18 years or so, we've been in a phase that has brought cooler than average waters to the eastern Pacific off of our coast here in California. And there's some evidence that this could also be switching in conjunction with this large El Nino. So all signs point to really warm water off the coast of California right now, and it could be that we're getting hit with all three of these things at once.
Any further questions here in the audience? Follow up, Steve.
Hi, I was wondering if Stephen Clark from Spaceflight Now again, I was wondering if one of you can clarify what happens with the Jason-2 satellite after Jason-3's launch. Does Jason-2 keep operating in tandem? What's the plan for Jason-2, basically?
So Jason-2 is in good health, which is good. So today the plan is to move, as I said, to move it to the interleaved orbit after 6 months. Then we have an approved program for 2 more years of operations. And then probably, as we did for Jason-1, we will decide to decrease the orbit for the end of life, because we won't let him die on the orbit, which is the working orbit for the following satellites.
If I could just add something to that as well. In the case of Jason-1, there was also a very strong scientific pull to continue to use the Jason-1 mission after moving it out of the primary orbit. It served as the interleaved satellite for a few years as well, as Jason-2 will in the next few years. And after that, it was moved to an orbit which had a very long repeat period and very closely spaced ground tracks. And this is very useful for helping determine the marine gravity field. And that helps us, in turn, figure out the shape of the sea floor. So we've used data from the Jason-1 end-of-life mission to help map out things like underwater mountains, trenches, and the general shape of the seafloor. And we hope in its very last days that Jason-2 will be able to provide us with a similar improvement in the marine gravity field.
Any further questions here at Vandenberg? You have a follow-up? Go right ahead.
For Mark, can you comment briefly just on how this mission has become such an international effort? There's so many international agencies involved on this. Can you just comment on that quickly?
Yeah, I think it's a transition from development programs to operational programs. So at the beginning, the development agencies started to do the work of developing systems. Then a demonstration was made that it could have an operational interest. Then, for instance, EUMETSAT stepped into Jason-2 and then increased again its role in Jason-3. And this happened also on the other side of the Atlantic, and this came in this way. And then the sustainability of the program, so the long-term aspect, meant in Europe that this was necessary to include it in a wider frame, which was the Copernicus program, and hence the involvement of the European Commission.
Actually, if I could add one thing to that as well. These missions, of course, were always international collaborations, all the way back to Topex Poseidon, which was a collaboration between NASA and CNES. So there's always been a strong spirit of international collaboration. And in fact, we have a science team that's 200 to 400 people strong, and they come from all over the world. So it's always had very strong international roots, I would say. The legacy has.
We're going to.
If I could add just one thing further. You would think that having a program that had 4 different agencies in it would be a prescription for disaster. In fact, it's been incredibly successful because we've worked together so well. And interestingly, for Jason-CS, ESA, the European Space Agency, is joining, so we're actually going to have 5 agencies involved. And I look forward to that because I think that that's just going to be, again, the kind of success that we've had.
We're going to take some social media questions now, and social media, if you do have questions, you can use hashtag AskNASA to send your question. And right now we're going to go to Steve Cole, who's been monitoring the social media sites, Twitter, and tell us, I think he has 2 or 3.
Okay, we have a few questions. Our first question is, what improvements have been made from Jason-2 to Jason-3 due to technological advances or lessons learned?
Well, I can say a few things about that. Well, I think one of the things to remember about Jason-3 is that it's almost identical to Jason-2. The improvements are really very small, and there are a couple of things in the operation, like we're going to be doing a calibration maneuver, which will allow us to get a much better long-term record of global sea level rise with a slightly better accuracy. But as you know, climate scientists and monitors of the climate, we really like our missions to be as similar as possible because we want them to build a long-term concrete record that's unbroken and provide we want our missions to tell us about changes in the ocean and not changes in technology. So in fact, although there are some very small improvements and modifications, the satellites are almost identical.
Okay, our next question. Could Jason-3 data be used to predict or detect rogue waves and help provide a quicker warning system to nearby ships?
That's a sampling problem which these satellites are not terribly well adapted to because they don't sample frequently enough over the entire ocean to detect what could be a very highly specific wave. However, I should actually mention that we've been able to detect tsunamis almost coincidentally, but we've actually, the big Indian tsunami was detected by our group in NOAA, and we were able to provide that information to modelers. So there are situations where we can detect individual waves, but I wouldn't call it a primary focus of the mission.
Will Jason-3 be part of the A train of Earth-observing satellites, or does it have its own specialized orbit?
Well, Jason-3 has its own special orbit that was very carefully chosen, in fact, to help us better understand and predict the tides. Because one of the major reasons that the sea levels go up and down is the pull of the gravity from the sun and the moon. This is very regular and very well predicted, but it wasn't well measured everywhere before satellites like Topex Poseidon were able to help us better understand the tides. So in fact, our orbit comes from a historical choice that was started with Topex Poseidon. And much like our desire to keep our satellites very similar from one to the next, we also wanted our orbits to be very similar from one to the next to help ensure that we're really measuring changes in the climate over the long term and not changes in our satellites and technology.
Let me just add something to what Josh said. In terms of being able to maintain continuity of the record, we're actually flying the two satellites together, the Jason-2 and Jason-3 satellites, for about 1 minute apart for 6 months. And this is exactly to measure the exact same location in the ocean with practically no time difference. So if we chose a different orbit for each satellite, we wouldn't be able to do that kind of lengthy intercomparison. And in a sense, we'd be putting a new satellite up in a sense, creating the potential for problems. So the orbit is a critical factor in maintaining the continuity of the record.
All right, we'll come back here. We got any further questions in the audience here? All right, and we have a follow-up. Good.
Hi, my name is Willis Jacobson. I'm with the Lompoc Record and Santa Maria Times. Can or will you guys care to comment on the launch vehicle and any attempts to land this rocket and possibly change, future launches?
That's actually going to be covered in our next briefing when we get to the pre-launch news conference. Those folks are on our second panel and can go into more detail about that with you.
I will say, though, that we're excited to get a ride to space, and we hope SpaceX breaks a leg. But not literally a leg, just in the figurative sense.
All right, that will conclude this briefing, and our next briefing will start in about 10 minutes, which will be the pre-launch news conference, and we'll discuss the launch coming up, the SpaceX Falcon 9, and the Jason-3 spacecraft itself. Thank you very much.